Okay, chi-squared test. Couple things. Degrees of freedom equals row minus 1 times columns minus 1. So we don't include the totals. So if you're looking, this one is a 2 by 4. So that's going to end up being 1 times 3. There'll be 3 degrees of freedom. Okay, we've got a table. On the second one, we've got a table. And on the third one, we don't have a table. So let's remember the ones with tables are the chi-square two-way test. There's two different names. There's independence and homogeneity. How do we tell the difference? Independence is one sample. Homogeneity, you take multiple samples from different groups. So let's read this one. This one says 63 students were selected. It doesn't say they selected first and then second grade students. They just put them in the table. So this one must be the chi-squared test of independence. Okay, so our null hypothesis would be that grade level and color choice are independent. The alternative then, of course, is that grade and color are dependent. Now, I don't want to be confusing, but this is also called this chi-square test of association. Independence is the same as no association, however, and dependent is the same as having an association. I know there was one on the multiple choice test. If you did that 2017 test, there's one that asks in the multiple choice which one are independent. And what you have to do is you just have to look. There's 5 multiple choice answers, and 4 of them they're dependent because the probabilities change for the different groups, but the one, they're exactly the same. So when probabilities don't change, that's independence. The probability doesn't change. What are our assumptions? Random, independent, data are counts. Then we need the expected cells to be greater than 5. Okay, we're going to fail on this one. We are going to run this test. We're going to find out that our expected cells are a little bit small. Is it really going to make a difference? We'll talk about that. So we're going to go menu 7-1. We're going to create a matrix. And we've got a 2 by 4 matrix. Okay, and we're going to store that into A. All right, so now we're going to go menu 6-7. We're going to run the chi-squared two-way test. And pretty much easy to run. We just put it on matrix A, and it runs the test. Now, after you run the test, we, of course, can get this stuff down. We got 2.2 and a p-value of 0.53. Our test statistic is chi-squared is 2.2. Our p-value is 0.53. But we should look at our expected cells. Our expected cells, of course, we go stat, expected matrix, var, expected matrix. And we write some of these down. We got 11, 12, 8, 8, 6, 7. I would write some of them down. We're going to see that I'd write all of them down, kind of dot it. So I'm not going to put these down, write them down when you're doing that on your AP exam. But we have 2 of them that are small. That would be a hindrance if we were going to reject the null. So some aren't. So we wouldn't be conclusive, but since this is so much greater than 5%, we're going to fail to reject the null. And it's not evidence that color and grade are dependent. Okay, what would you do on the AP test? They could have you combine some categories. So maybe we put red and yellow together, and I still don't think we're going to find even if we combine these two and we make it 10 and these two and make it 11 for red and yellow, that we're not going to find much of a difference. Okay. So the next one, in 2018, Mr. Weber and Mr. Becker collected data to see if there was a difference in the number of AP classes taken by students in their classes. Now, okay, AP Stats is going to be treated as one group and Calc as another group. Okay, so again, we've got a 2 by 6. So 2 and 6, we're going to take 1 times 5, going to be 5 degrees of freedom. You might have to know that. Notice we had 3 degrees of freedom back here. Okay, but we'll go menu, 7-1. And create a 2 by 6 matrix this time. Type these in, 16, 17, 9, 5. 2, 1. Going to have a familiar, oh no, no, this one we're not going to quite meet it, but we're going to go ahead anyway. 5, 7, 12, 8. Bad example on my part to not get those to work out. 8, 8. Okay, so number of AP classes taken by their students. I should change that 1 to a 2 or something like that, but we're going to proceed anyway. So a lot of times if you don't meet an assumption, it gives us that opportunity to say, well, we're going to proceed with caution, meaning maybe our results aren't valid. Store this one in B this time. We'll go menu, 6, 7, 8 again, B. This one's going to be highly significant. If we look at our expected cells, we press our stat expected matrix, and we see they're all well above 5, except for the last two. We're going to be at 4.5 roughly for both of those. So we'll just proceed. Anyway, what is our null hypothesis? Our null hypothesis is that stats and calc, the two groups, have the same proportions in each category. Okay, that the groups have the same proportions in each category. It doesn't mean that they're all the same proportions. For instance, maybe the proportion of 1 is supposed to be, 20%, but then it'd be 20% for both, 30% twos, something like that, whatever it might be. But the alternative, that stats and calc have different proportions in some categories. Okay. So again, random, independent, data or counts. The expected cells, one of them is less than 5, so we'll proceed with caution. But this one is the chi-squared test of homogeneity. Remember, homogeneous means the same. Are the proportions the same? We got a chi-squared value of 20, a p-value of approximately 0. 0 is less than 5%. We will reject the null. And we have evidence that the proportions in some categories differ. For stats and count. Okay. Now again, if that happens on the AP test, you could be asked to combine them. Maybe we would combine the 5s and the 6s, and then we would end up, if we did that, even though this one would have a total of 3, this would have 16. When you do the expected value, it's going to be about 9.5 in each of those, and we're going to be okay. All right, the last one, the chi-squared test of goodness of fit. Okay, it says in the past, 60% of graduating seniors have gone on to a 4-year program. Now remember, the goodness of fit, that one goes into a table. Okay, so we're going to call this one X and this one F, and 60% have gone on. So I'm going to put my frequency list in here. 22% have gone to a 2-year program, so I'm going to put 0.22. 4% have gone on into the military, and the rest in the workforce. So we're going to have to figure that out. That's 86%. So 14% going into the workforce. Okay, so in a random sample of high school seniors, we find 85 are going into a 4-year program, 64 are going into 2-year schools, 4 are going in the military, and 50 into the workforce. Okay, now you're going to have to come up with this total. That's 203 is our total. So over here in this row, I'm going to call this one double F, FF for frequency, because I'm going to do some multiplying with this. And we'll call this one the expected cells. XP cannot XP, all right? So we're going to take FF and multiply it by 203, the total. Remember, you have to take your percentages times how many you sampled. And now those are our expected cells. Now we should write those down. I did a poor job on the first two of writing them down. I'm going to write them down this time. 121, 44, 8, and 28. All those are bigger than 5. So we're going to assume it was random, independent, and data are counts. Our null hypothesis, 2 ways you can do it. You can say our proportion of 4-year is supposed to be 60. Our proportion of 2-year is supposed to be 22. Our proportion of military is supposed to be 4%. Our proportion of workforce is supposed to be, what was the rest? 286, 14. Or the proportions match the historical data. So either that could be the null or that, but then the alternative, remember, is at least 2 proportions differ. This is the chi-squared goodness of fit test. So how do we run the goodness of fit test? We go on here, menu 6, 7, and number 7, our observed list, I have it in X. Expected list is XB. Our degrees of freedom, since there's 4 categories, it's just N minus 1, or categories minus 1, excuse me. And we get 3. So we get 37.97. Now, one thing I want to point out, look at our p-value. It's not 2.86, it's 0.00000. Okay, so that's roughly 0. Hopefully that's happened to you enough times that you're not going to get that wrong. Our chi-squared is 38. P-value is approximately 0. 0, of course, is less than 5%. If it's less than, we reject the null. And we have evidence for HA, which at least 2 differ. Okay, those are the chi-squared tests. Make sure that you get the chance to review those. Let's jump into a linear regression test. What is the least squares regression equation? Remember these coefficients. This is A, this is B. If you go on your statistical formula page, where's that one at? Oh. Should have, here we go. Y hat equals A plus BX. Remember, they just give you A and B, and then this is always X. So sometimes you have to look where Y is, but it says it's years of experience against productivity. So our productivity is what we were trying to whatever they've rated that as, hat equals 1.147 plus 3.42, that's A, that's B, times X, years experience. That is something everybody should be able to do if you see those two coefficients. Explain the slope in context. That's 3.42. We predict 3.42 more in productivity for 1 more year experience. Remember, it's 3.42 over 1. This is Y, and Y goes with the productivity, and this is X. X goes with the year's experience. Create a 95% confidence interval for the slope. Now, you are going to need your t-table. It says there's 25 employees, so we got to
Good morning, Warriors. Due to the inclement weather forecasted for today,
Sorry, there's an announcement about inclement weather going on here. Always happens every time I do a video, so I apologize.
Track, the meet at Brandon Valley has been postponed.
23 degrees of freedom.
WHS softball will play Jefferson.
We're going to go across from 95% confidence.
That will be a varsity-only game at the Sanford Sports Complex. There will be no JV game tonight. So again, tennis is postponed, track is postponed, varsity softball will play at 6 o'clock at Sanford Sports Complex. No JV softball game tonight. All other activities are on as scheduled. Students, see your activity leader if you have any questions. Have a great day, Warriors.
Apologies for that. Confidence interval, statistic, plus or minus critical value. Your critical value is your T star. So our statistic is our B, 3.42 plus or minus 2.069 times 1.83. There's no dividing by the square root of n to get this value in here. We do the negative, we get negative 0.37. Then we do the positive value, 7.2. So we have to do the sentence, I'm 95% confident that the true slope between years of experience and productivity is between negative 0.37 and 7.2. Is there evidence of a slope based on that? Since it could be zero, zero's in the interval, there's not evidence. Make sure that you would write the sentence, I am 95% confident, and the bell's going to ring again, that the true slope is between this and this. Explain R squared. R squared, we've got 87.3%. Make sure you review that. 87.3% of the variation in productivity, which is Y, is explained by years experience, which is X. All right, last one. A lot of things in here, just kind of a quick gloss over review. Is there evidence for a slope? We would say the null, B equals 0. B is the slope for productivity and years. Okay, now the assumptions, a lot of times they'll say on this the assumptions are met, but the assumptions, I will briefly go over them. You know, a lot of times on this one, they'll give you a graph. Is the graph linear? Does it look linear? Are the residuals, they have equal variance? In other words, if you saw a residual plot, they're kind of equally scattered, not thinning or thickening on either end. That would look something like this with the residuals where they're getting thinner, closer together on one end or the other. And then we would run into doing a linear regression t-test. Now, usually the linear regression t-test is here. A lot of times it gives you the t-score and the p-value. I don't have it there. I didn't put it there on purpose. So your t-score, you would take your slope, which is 3.42, and you subtract 0. So whatever that null is, since we're saying, is there a slope? 0 is no slope. And then we would divide by 1.83. Okay, so our t-score is going to be relatively small. And we get 1.86. Okay, now you don't have to draw a curve, but here's where we're at. 1.86, you're going to have to use a TCDF. I know we don't use that very often, but we're going to go menu 6.5, number 5, the TCDF, from 1.86 to 99999, 23 degrees of freedom. Remember, with the linear regression test, it's n minus 2, and that gets us 0.037. However, since our alternative is not equal to, we have to shade from negative 1.86 on down as well. Okay, and we will double that p-value. So we get 0.075 or 0.076. And 0.076 is actually greater than 5%. Why do we use 5%? It's standard alpha. Use 5% on the AP exam the whole time. So we will fail to reject the null. And we have not enough evidence for a slope. If we had only done greater than, since it's not equal to, it doubled that p-value. If we'd only done greater than, then we would have gotten that 3% and we would have rejected the null and said there is evidence of a positive slope. So it all depends on the alternative. You can't change it after the fact. That would still say not equal to, but hopefully that's some good things that you've reviewed for the AP exam. Best of luck on the AP exam next week.